distribution can be used to test whether observed data differ significantly from theoretical expectations. For example, for a fair six-sided die, the probability of any given outcome on a single roll would be 1/6. The data in this table were obtained by rolling a six-sided die 36 times. Clearly, some outcomes occurred more frequently than others. For example, a 3 came up 9 times, whereas a 4 came up only 2 times. Are these data consistent with the hypothesis that the die is a fair die? Naturally, we do not expect the sample frequencies of the 6 possible outcomes to be the same, since chance differences will occur. So, the finding that the frequencies differ does not necessarily mean that the die is not fair. One way to test whether the die is fair is to conduct a significance test. The null hypothesis is that the die is fair. This hypothesis is tested by computing the probability of obtaining frequencies as discrepant or more discrepant from equal frequencies as the frequencies obtained in the sample. If this probability is sufficiently low, then the null hypothesis can be rejected. The first step in conducting the significance test is to compute the expected frequency for each outcome given that the null hypothesis is true. For example, the expected frequency of a 1 is 6, since the probability of a 1 coming up is 1/6, and there are a total of 36 rolls of the die. The expected frequency is 1/6 times 36, which equals 6. Keep in mind that the expected frequencies are expected only in a theoretical sense. We do not expect the observed frequencies to match the expected frequencies exactly. Continuing the calculations, let E be the expected frequency of an outcome and O be the observed frequency of that outcome. For each row, subtract the observed from the expected, square the difference, and then divide by the expected frequency. For the outcome 1, the expected minus observed is 6 minus 8, which equals -2. Square that and you get 4. Divide 4 by the expected frequency of 6, and you get 2/3, or 0.667. Next, you add up the expected minus observed squared divided by expected column. This total is distributed as chi-square. The degrees of freedom is equal to the number of possible outcomes, which we call k, minus 1. Since there are 6 possible outcomes for the die, the degrees of freedom equals 5. Recall that the mean of a chi-square distribution is its degrees of freedom. In this case, the mean is 5. Therefore, the value of chi-square is similar to the mean of the distribution. In other words, the deviations from the expected frequencies are about what would be expected if the null hypothesis were true. The chi-square calculator can be used to determine that the probability of a chi-square of 5.33 or larger is 0.3766. Therefore, these data are consistent with the null hypothesis that the die is fair. Of course, the data do not show that the null hypothesis is true. They just don't contradict it. A common use of the chi-square distribution is to test whether a distribution deviates from normality. In this example, we test whether the variable university GPA in the SAT and college GPA case study deviates significantly from normal. The first step is to divide the distribution of GPAs into discrete categories. Then, the number that will be expected in each category is computed, assuming the distribution is normal. Chi-square is then computed based on the differences between the expected and the observed frequencies. The first step is to standardize the GPAs so that they have a mean of 0 and a standard deviation of 1. We then compute the expected frequencies for 4 categories: those with standard scores less than -1, those between -1 and 0, those between 0 and 1, and those over 1. There is nothing special about the choice of 4 categories. We might have chosen 5 or even 10. From the normal distribution calculator, we can compute that 0.159 of the distribution is below a standard score of -1, and 0.341 is between -1 and 0. Since the distribution is symmetric, 0.341 of the scores are between 0 and 1, and 0.159 of the scores are above 1. These are the proportions expected if the distribution is normal. All we have to do to get the expected frequencies is to multiply the expected proportions by the number of students, which is 105. For example, the expected proportion of students with scores above 1 is 0.159. Multiplying by 105, we get the expected frequency of 16.695. The observed frequencies are computed by counting the number of students with standardized GPAs in the various intervals. For example, only 9 students have standard scores above 1. It is clear that the distribution deviates from a normal distribution. The greatest deviation is that only 35.805 students were expected to be between 0 and 1, while the actual number in that interval was 60. The significance test is computed by calculating the expected minus observed squared divided by expected for each cell and adding the results together. The resulting sum of 30.09 is the chi-square statistic. The degrees of freedom is 4 minus 1, which equals 3, since there are 4 categories. The chi-square calculator shows that the probability of obtaining such non-normal frequencies if the distribution were in fact normal is less than 1 in 1,000. Therefore, the null hypothesis that the GPAs are normally distributed can be rejected. Now add the values. The resulting sum of 30.09 is the chi-square statistic. The degrees of freedom is 4 minus 1, which equals 3, since there are 4 categories. The chi-square calculator shows that the probability of obtaining such non-normal frequencies if the distribution were in fact normal is less than 1 in 1,000. Therefore, the null hypothesis that the GPAs are normally distributed can be rejected.